So thank you all very much for coming to this our last Canvas meeting of the year before the winter break. I'd like to start things off by taking a moment to acknowledge that I'm coming to you today from NRC Hertzburg, which is located on the traditional territories of the Coast Salish and Lekwungen-speaking peoples here on Vancouver Island, and the Syilx Okanagan-speaking peoples in the Penticton area, who are the custodians of the respective lands and waters. These areas have long been the gathering places of the First Nations well before the arrival of Europeans. We are grateful for the opportunity to live, work, collaborate, and learn here, and we respect the continued connections with the past, present, and future, and the ongoing relationships with Indigenous and other peoples in the British Columbia community. We invite all attendees today to reflect on the relationships you have to the communities that inhabit this land and share the night sky and wonder. Today, we're going to be hearing from Dr. Keir Rogers, who is a theoretical and observational cosmologist, currently a Dunlap Fellow over at the University of Toronto. So before moving to Canada, he was an Oscar Klein Center Fellow at Stockholm University and was awarded his PhD at University College London. And today he's going to be telling us about cosmic probes of dark matter physics. So why don't you take it away, Keir?
Great, thanks, Tyrone. So yeah, thanks for the introduction. I'm very pleased to have this opportunity to share my work with you all. And the title of the talk is Cosmic Probes of Dark Matter Physics. And it's about looking for the signatures of the microphysical properties of dark matter, how it affects the universe on the larger scales in the cosmic microwave background and the cosmic large-scale structure. So my work is about trying to connect models of cosmology to models of particle physics, in particular in this case, searching for the dark matter. We know that 80% of the matter in the universe today is not made of particles that we understand, but we have no conclusive evidence as to the fundamental nature of that dark matter. And there are many well-motivated dark matter models that cannot be tested by traditional experimental approaches at colliders or by direct detection. And so these models are, as of today, largely unexplored. But because of the continuing non-detection of the traditionally preferred candidate, the WIMP, the weakly interacting matter particle, the dark matter community is turning to consider a wider range of models and considering new experimental approaches to look for them. And cosmology has the ability to detect the signatures of particularly well-motivated models. And so in particular in this work, I use the Lyman alpha forest as a tracer of the cosmic large-scale structure, which is very sensitive to cosmic structure on the smaller scales we can currently access in the linear matter power spectrum. And I'll spend a chunk of the talk talking about the specifics of our analysis method, which is a way to compare our most accurate models of the universe using cosmological simulations, comparing those to data using a machine learning accelerated method called an emulator to make the comparison. And then at the end, I can present new, stronger bounds on these dark matter models that now, in fact, significantly disfavor some of the more interesting parts of their parameter space. So dark matter candidates are well motivated at a very wide range of masses. So this is a very schematic, not to scale view of the landscape of dark matter models on the wide range of masses. So I have the very lightest masses on the left. These masses are so small that their corresponding wavelengths would be on the scale of the cosmic horizon. And then this goes through to the various heaviest masses at the Planck scale. And we have the WIMP, which is around GeV to about 100 TeV masses at the unitarity limit. And then we have other well-motivated regimes, for example, dark matter particles which are lighter than the traditional WIMP, with masses less than a gigaelectron volt down to the warm dark matter limit at keV. And in particular, I highlight this low mass regime where boson particles called axions could exist. and in particular, what I call ultralight axions, anything lighter than about 10 to the minus 18 eV. And in particular, I highlight a canonical region in the mass at 10 to the minus 22 eV, which is particularly well motivated and is a target for cosmological tests. So let me start with the axion. The axion, as it was originally proposed in the late 70s, was to resolve an outstanding problem in the standard model of particle physics called the strong CP problem. And this is the fact that within quantum chromodynamics, there's a parameter which is experimentally observed to be highly fine-tuned with a value very, very close to 0. And in order to resolve this fine-tuning problem, the proposal by Petrie and Quinn was to elevate this parameter to the role of a dynamical field, the Petrie-Quinn field. And then you could construct a potential such that this number would naturally be driven towards a very small value. So you see an illustration of that here, where you would have a hat-shaped potential, and at some energy scale Fa, the field will drop into the brim of this hat. You have an angular degree of freedom, and then around the QCD phase transition, the symmetry in this would break, and the field would oscillate around the bottom of this potential, and it would tend towards this small value to correspond with experimental constraints. But it was quickly realized that this would also produce particles, which were called axions, in the oscillations of the field around the bottom of this potential, and that these were produced in sufficient abundance that they were viable dark matter particle candidates also. And to solve the QCD problem, the strong CP problem within QCD, and be a dark matter candidate, you have an inverse proportion between the particle mass and this energy scale Fa. But extending from that, it was realized that a wider class of axion-like particles were generically produced in many beyond standard model theories, in particular in string theory. So now the mass and its energy scale are both free parameters of the model. And in particular in string theory, you have the prediction of what's called the string axiverse, the idea that you would produce many different axions, each of a different mass. This would arise from the compactification of the extra dimensions you get in string theory. So this plot is showing a view of the number of axions produced in various configurations of this compactification, and you typically get on the order of between about 30 to 100 axions for a given configuration. So you would abundantly produce particles that are also viable dark matter candidates. In particular, they, depending on the wide range of configurations you can consider, they generically produce very light particles that we call ultralight axions. And by this, I'm defining anything lighter than about 10 to the minus 18 electron volts. I've set a lower limit at about 10 to the minus 27 electron volts, because anything lighter you would actually behave akin to a cosmological constant for a significant fraction of the universe's expansion history. And so you have additional effects from behaving like dark energy, which is also extra constraining on the model. So the key fundamental feature that we're searching for in cosmology to constrain these models is the fact these particles are so light that they have de Broglie wavelengths of astrophysical sizes. So for example, if you take a 10 to the minus 22 eV electron volt axion, you have in the intergalactic medium a de Broglie wavelength, or we call this the quantum pressure scale, on the order of about 100 kiloparsecs. And so these plots are showing slices through simulations, in the left-hand case for ultra axion dark matter and the right for cold dark matter. And you see in the axion case, much less small-scale structure, because this doesn't form on scales smaller than this quantum pressure smoothing scale. So the filaments are smoother than in the cold dark matter case, the standard WIMP-like dark matter candidates. There's also motivation for ultralight axions to provide new physics to resolve various anomalies and tensions within the cosmological model. One of these is addressing the small-scale crisis, which I will talk about a bit more in a few slides. But also there are hints that other tensions like the Hubble tension could be alleviated by a fraction of the dark matter being comprised of these light axions. Also the S8 tension, the tension in the amplitude of fluctuations between the CMB and galaxy weak lensing data perhaps could be resolved by having a fraction of the dark matter in these particles. So there are theoretical motivations to go after this very low mass regime by looking for this suppression in the growth of small scale structure. And because these axions will be produced on many different masses, there's a generic reason to believe that we would have a mixed dark matter scenario where different axions are contributing a different proportion to the dark matter energy density. And the first case to consider then in testing this theory is to consider a single axion species with one mass and the rest of the dark matter just behaving as standard cold dark matter. And the matter power spectrum is very sensitive to these mixed dark matter models because we're looking for this suppression scale. And that's illustrated in this plot, where we're seeing the matter power spectra in the top panel for axions of different masses from 10 to the minus 30 to 10 to the minus 26 eV. And then the different colored lines is increasing the fraction of the dark matter density in axions from 0% at purple up to about an 8% fraction in yellow. And then in the bottom panels, you see the ratio to the cold dark matter power spectra. And you see two effects, which is as I increase the axion mass, the wave effects manifest on smaller scales, i.e. larger wave numbers K. So the scale gets pushed out. But also as I increase the number of axions, the fraction parameter, the strength of the suppression increases as well. And these two effects are not entirely degenerate. And so you can break that degeneracy. And in particular, the gray band shows the range of scales probed by the Baryon Oscillation Spectroscopic Survey galaxy clustering data. And so using galaxy data in combination with the CMB puts tight constraints on this particular range of masses for these fractions. And so there was an analysis led by a PhD student in Toronto, Alex Legui, who did this. He looked at constraints on the axion mass on the x-axis and the axion energy density, omega A, on the y-axis using Planck CMB data. So CMB is mostly constraining through the lensing power spectrum, because then you're sensitive to this, this suppression in the matter power spectrum. Using BOSS galaxy clustering, the monopole and the quadrupole of its clustering, and then a combined analysis of the two. And you see that at all the masses, combining BOSS and Planck improves the bound over CMB alone up to a factor of about 4.5 times. So we now set strong sub% constraints on the number of axions in this very low regime for its mass using current data. And so the heaviest mass that we saw there was about 10 to the minus 25. And to start to push up to heavier ultralight axions, we need to use smaller scales in the matter power spectrum so we can look for these smaller scale suppressions from these heavier axions. And we can do that using galaxy weak lensing data. So this is a weak gravitational lensing of the shapes of galaxies. These are magnified and distorted by massive gravitational structures in between the object and the observer. And by measuring the correlation in the amount of distortion, we're sensitive to the dark matter distribution directly rather than indirectly with the galaxy clustering, where we have to model how galaxies populate the dark matter halos. Using the shear correlation function, we're more directly sensitive to the dark matter distribution itself. And we can look for this suppression on smaller scales using weak lensing. And so this is showing an analysis, this time led by a postdoc at University of Göttingen, Mona Dentler, who did a joint analysis of Planck CMB data and dark energy survey weak lensing data. And the combined constraint improves over them individually and sets a lower limit on the allowed range of axion masses at 10 to the minus 23 electron volts. this is now only considering the case where axions comprise the entirety of the dark matter. We need improved modeling of the mixed dark matter case for this heavier axion mass regime. And I will talk about how to address that later on. So we've got very tight constraints right up to 10 to the minus 23. But as I indicated earlier, there's a canonical range of masses at 10 to the minus 22, which is particularly well motivated. And part of that comes from theory itself. So there are a couple of analyses that I want to highlight here. On the left is one where analysis was done looking at the positive distribution on the axion mass using priors on axion parameters drawn from string theory, using also existing cosmological constraints, and they found the posterior peaked very strongly at this 10 to the minus 22 EV mass range. And it was also pointed out in this important paper by Lam Hui et al. That a 10 to the minus 22 EV axion would give a decay constant, this energy scale at which the field drops into the hat potential, somewhere between the reduced Planck and grand unified scales. So that would draw a connection between the production of this dark matter and grand unified theories, which was theoretically motivates this, this mass range. And there's also these astrophysical motivations, which I talked about also. So in particular, ultra axions are invoked to resolve the so-called cold dark matter small scale crisis. The small scale crisis is a collection of discrepancies between the predictions of cold dark matter only simulations and observations on galactic scales. So it includes, for example, the cusp core problem, where CDM only simulations produce cusp-like density profiles in the central regions of dark matter halos, whereas we observe more shallower core-like profiles. The so-called missing satellites problem, where historically fewer satellites were observed than were predicted in CDM-only simulations, and correlated to that is the too big to fail problem. And axions are invoked to resolve this because at 10 to the minus 22 EV, their de Broglie wavelength in the centers of halos would be on kiloparsecs, and so you would smooth out the dark matter distribution and produce cores which would match observations. And the quantum pressure scale would be on the order of megaparsecs, and this would correspond to a strong suppression in the subhalo mass function. It would explain why we didn't historically observe many low mass satellites of the Milky Way. Now, there's been improvements in how we model the formation of dark matter halos, which have shown that it's very important to account for the effect of baryons in these simulations. So we can produce cores using baryons. And also there's been a lot of new data recently that has discovered many more low mass satellites. And so the missing satellite problem has been resolved to an extent. But now we can turn the problem around and use these observations on small scales to put constraints agnostically on ultra axion dark matter as motivated from theory. And so we're going to look for this suppression scale in arising from ultra axion dark matter using a tracer of the cosmic large scale structure called the Lyman alpha forest. And so this plot is showing something similar to what we saw before. So it's the square root of the ratio of the linear matter power spectra for ultra axion dark matter over cold dark matter case, function of wave number k. And you see each one of these lines is for a different axion mass. You always get this very sharp cutoff in the linear power. And as I increase the axion mass, the wave effects manifest on smaller scales. And so the cutoff gets pushed out to larger values of k. And it follows this rather simple monotonically increasing function, the cutoff scale k half proportional to this. And so the Lyman alpha forest, if you want to improve our lower limit on the allowed range of axion masses, you want smaller scales, and the Lyman alpha forest gives us the smaller scales that we currently access in the linear matter power. It's also a very good tracer of linear order perturbations because it's sourced in intergalactic gas that mostly sits at mean cosmic density. So there's less nonlinear effects which erase this cutoff signature. We also observe it at high redshift, which is around 5. So again, there's less cosmic time for nonlinearities to erase this signature. And using high resolution measurements of this feature, we were able to probe small scale density perturbations. Okay, so I just want to return now to the model landscape and just highlight one other range of models that we've been in particular looking for and putting bounds on, and that's this light dark matter regime. So anything less than about a GeV in mass. And so one of the main ways to look for WIMPs that things heavier than a GeV is using direct detection experiments. So these essentially are experiments where you get a big tank of typically a noble gas liquid. So xenon is a popular target material. You place it deep underground, so you're shielded from background sources. You put it in a large concrete shielding material, as is indicated here. And then you sit and you wait for dark matter particles, which are going around the dark matter halo. As the Earth moves through this dark matter wind, these dark matter particles will hopefully hit one of the atoms in this target material, give it a little kick, ionize an electron, you put an electric field over it, the electron drifts up, and then you have photo multiplier tubes to look for scintillation lights at the top. Now, these are big experiments. So this is a picture of the xenon 1-ton experiment. This is all to scale. So these are offices on the right, and then the whole experiment is on the same scale as 3 stories of these offices. And so the xenon 1-ton and many other experiments looking for direct detection of WIMP nucleon interactions. But these are typically limited in their ability to look for any dark matter lighter than about GeV. And that's basically because any lighter dark matter particle, the kick it gives, the nuclear recoil it induces, doesn't produce a strong enough signal to be detected. And so this plot is showing an exclusion at 2 sigma on the cross section between the WIMP particle and the nucleon, protons and neutrons. It's a function of WIMP mass. So you've got 1 GeV up to 10 TeV. The green area is current limits. So these are very up to date from earlier this year. So xenon 1-ton sets the strongest limits now. And then the lines are showing various projected sensitivities from upgrades to these experiments and new experiments coming online. And it's a very exciting prospect of now reaching what's called the neutrino floor, where you are limited by a neutrino flux in your sensitivity. But this is limited to masses greater than a few GeV. And even on lower masses, projected sensitivity is no better than about 100 MeV with upcoming upgrades. So we need a different way to look for dark matter that would be lighter than this mass scale. And the collisions between dark matter and protons that we can sit and wait for in underground laboratories happened abundantly in the very early universe, when the universe was smaller and hotter and denser. And the imprint of these primordial dark matter proton collisions is visible in the cosmic large-scale structure today. Essentially, you have collisional damping of the growth of small-scale structure. And so this plot is showing, again, something similar to what we saw before. Now it's the ratio of linear matter power spectra for a non-cold dark matter model in ratio to cold dark matter as a function of wave number k. The black line is one of these ultralight axion transfer functions that we saw before with a very sharp cutoff. And then the colored line shows the small-scale suppression from a dark matter proton cross-section of different values. I should say specifically, we're considering the case where the cross-section is independent of the relative velocity between the dark matter and baryon fluids. And you see that it's a similar effect, so it's a small-scale suppression, but the scale dependence of the suppression is markedly different. It's a much shallower suppression arising from DM proton collisions. And as I reduce the cross-section, the effect manifests on smaller scales, i.e. larger wave numbers. So if we want to expand our discovery space for light dark matter, we need to, again, access smaller cosmological scales. So this plot is now showing the suppression scale as a wavelength in parsecs as a function of proton DM cross-section on the y-axis and dark matter mass on the x-axis. And you see that smaller suppression scales will improve your upper limit on the allowed range of these cross-sections. In particular, I point out that we're probing masses less than this 100 MeV to GeV mass scale to which direct detection is limited. Okay, I'll pause down. The next section of talk is talking about the Lyman alpha forest, so perhaps I'll just pause a second if there's any questions about what I've said so far.
I have a quick question.
Go ahead.
You have you talked about at the beginning. You hinted at you have the range of axion masses, and the lightest masses could possibly explain dark energy, and the not so light masses could explain dark matter. So, is it possible there is a range, and then everything's explained, dark energy and dark matter?
Yes. So, if you get to very light masses, 10 to the minus 32, it's completely indistinguishable from a cosmological constant. So observationally, there would be no way to distinguish the two. At an intermediate stage, so essentially the axion always behaves like dark energy very early on. And then once the oscillations kick in, then it behaves like cold dark matter, but with this on a time averaged regime. And so there's a kind of intermediate range less than 10 to the minus 27 where it would behave like dark energy early on, but then it would transition to dark matter, but this would occur after matter radiation equality. But the constraints I showed using CMB and galaxy clustering put very tight constraints on this particular mass range. And you get constraints on the dark energy regime also from the ISW effect in the CMB data, so producing large scale power in the angular power spectrum. So theoretically, in principle, it could explain all these things, but there are essentially very tight observational constraints.
Right, thanks.
Awesome. If there are no other questions, maybe go ahead.
Cool. No worries. Great. Okay, so I've been referring to the Lyman alpha forest as a very good tracer of the small scale structure in the cosmic density field. And so what is the Lyman alpha forest? Well, it's an absorption feature we see in the spectra of high redshift quasars. And this film illustrates how this signal forms. So what you're seeing is the quasar spectrum. So quasars are these very bright objects in the early universe that we can detect more easily than other objects at such early times. And the spectrum, when the light is emitted from the quasar, is this broadband, smooth emission spectrum. But as the photons interact with clouds of neutral hydrogen gas in the intergalactic medium, absorption occurs in the Lyman series. So what you're seeing here is the Lyman alpha absorption at 1260 angstrom, Lyman beta, Lyman gamma, Lyman delta through to the Lyman limit. But because the universe is expanding, this is all being continuously redshifted. New absorption always occurs at the rest wavelength. And so we end up seeing a forest of lines where the position and the strength of that absorption is a map of the distribution of the neutral hydrogen gas along the line of sight to the quasar. And that in turn is a mapping of the distribution of the dark matter along the line of sight to the quasar. And if we have many of these quasars, then we start to build up a three-dimensional map of the distribution of the dark matter at high redshift near where these quasars are emitting. And so we can look for this cutoff in the dark matter distribution as it manifests in the strength of the absorption in the Lyman alpha forest. But that means that we need to very carefully model how the intergalactic gas is tracing the dark matter. And the first effect to consider is that we are not directly tracing the dark matter, but rather the baryons. The absorption is coming from neutral hydrogen, and this has a finite pressure, unlike the dark matter. So what you're seeing here is slices through hydrodynamical simulations. On the left hand, the projected density of the baryons, and on the right, the projected density of the dark matter. And you see that on large scales, they are tracing each other, but because of the finite pressure, there is a smoothing scale associated with that pressure, the G scale of the gas. And so to look for intrinsic smoothing in the dark matter, we need to very carefully marginalize over uncertainty in the extent to which the baryons are pressurized, which is a function of the amount of energy injected into the gas during the reionization process, which is just completing before the redshifts at redshift 5, at which we are observing the Lyman alpha forest. And the other effect we're sensitive to is the instantaneous temperature of the gas. This has two main effects. One is that the temperature sets the recombination rate from ionization back to neutral hydrogen. And it also, each of these absorption lines will be thermally broadened by the finite temperature of the gas. But the problem is simplified because in the IGM, there's a very tight correlation between the temperature of the gas and its density. And that's illustrated in this plot where we have the distribution of particles from a hydrodynamical simulation with their temperature on the y-axis and baryonic overdensity on the x-axis. And bearing in mind that this color bar is logarithmic in scale, you can see that the vast majority of the IGM lies along this very tight linear relation between the two parameters. And this is the gas that is sourcing the Lyman alpha forest. And so in marginalizing uncertainty in the temperature of the gas, we need just two parameters, the mean temperature T0 and the slope of this temperature density relation tilde gamma. And so these parameters are both affecting the small scales of the power spectrum correlations in the Lyman alpha forest. And so here you're seeing the effect of T0 and U0. U0 is the integrated energy injected into the IGM per unit mass, and it's a very strong tracer of the pressure smoothing scale. And we're seeing the effect of these parameters on the flux power spectrum correlations in the Lyman alpha forest. So you've got the flux power in the top panels, and the bottom panels show the ratio of the flux power to a fiducial value. And you see at the top that as I increase the temperature, I smooth out the small scale power spectrum. And as I increase the amount of energy injection, I also smooth out the small scale power spectrum. So again, to look for smoothing from the dark matter particle nature, I need to carefully marginalize over uncertainties in these effects. But we can exploit the fact that the smoothing arising from gas astrophysics changes differently with redshift and scale with respect to the two parameters here and also with respect to the dark matter. And this will help to break degeneracies in our model. So robust dark matter bounds must marginalize the astrophysics of the IGM. And our most accurate model of the IGM requires the calculation of cosmological hydrodynamical simulations. But these typically take on the order of about 3,000 CPU hours per simulation. And we need these to span the about 12-dimensional parameter space, accounting for all the nuisance, cosmological, and IGM parameters. And so standard approaches to parameter inference will not suffice. If you try to sample a posterior distribution with an MCMC chain, and you wanted to run a new simulation at each step in that chain, that would suggest running millions of these simulations, and that is computationally infeasible. And the solution is instead to construct a machine learning model called an emulator, which is computationally cheap to evaluate. So I can predict flux power spectra in a fraction of a second, and then I can then plug that into my MCMC sampler. But it has the accuracy of hydrodynamical simulations because it's been trained on a training set of hydro sims. So again, I'll just pause a second because the next section of the talk is going to discuss how we build this emulator model. So if there's any questions on the IGM model, I'm happy to take them also.
Questions on the IGM model? So how would you tell the model of, sort of a naive question, how would you tell the model of heating of the IGM do you have built into these hydro simulations? So like, do you include things, you know, I guess I always worry about things like X-rays and stuff like that for creating these partially ionized zones. So could you maybe comment on that a little bit?
Yeah, absolutely. So the approach we take is to be is to be agnostic to the sources, the specifics of reionization. So things like whether it's X-ray driven or otherwise. And so we build a very flexible parametric model instead. So we vary parameters that describe a reasonable range of observational features. So we're varying the temperature of the gas and the amount of energy injection, and then we set priors on those parameters that will cover the wide range of possible physical sources of that heating.
Okay, and then you're learning over these, like that's included in your parameter space.
Exactly. So then, so then for this emulator part, we will set up a set of training simulations that span that parameter space, and then train the model on that. So it's across the full parameter space.
Okay, well maybe that bridges well into the next section. So let's go ahead. Thanks, Keir.
No worries. Exactly. So we're going to build this, what's called a surrogate model for the power spectrum. And so the next section is going to be a bit more technical. I'm going to talk about the actual model that we use. So what we use is something called a Gaussian process. And that's a way to smoothly and probabilistically interpolate between the few trading simulations that you are able to run. And I'm going to illustrate this using a simple one-dimensional toy model, but we do test the full model, which is predicting the flux power spectrum as a function of all these dark matter, IGM, and cosmological parameters. So if we start with the top panel, I have a single function output, proxy for the flux power spectrum. It's a function of a single parameter, proxy for all these cosmological parameters. The blue dashed line is the true function we're trying to predict, but we only have information where there are black crosses. These are training points. So we train the emulator model on the training information. We optimize its hyperparameters, and then use it to make a prediction as to what the true function is. And that red line is the mean of that prediction. And what's particularly nice about this model is that it's probabilistic. So we get a measure of, we get an empirical estimate of the uncertainty in this prediction, which is the red band. And we could then use this to carry out a likelihood analysis. So the bottom panel, the blue dashed line is the likelihood of some mock data if we knew the true function response. And the red line is our estimation of the likelihood, given that we only have the emulator prediction. And the consequence of having uncertainty in the emulator prediction is to broaden the peak of the likelihood. And so you will generally weaken your parameter constraints if you have an uncertain emulator model. And so the key thing now becomes how best to decide where you should run the few training simulations that you can run according to your computational budget. So we use this idea called active learning, where we're going to iteratively build up the training set, add simulations in iteration. And at each step, we define what's called an acquisition function to decide where we should choose the next training point. So this particular technique is called Bayesian optimization. And this acquisition function peaks where the emulator uncertainty is high, so that we get better characterization of the objective function. But it also peaks where the likelihood or the posterior probability is high, so that in a data-driven way, we tend to prefer adding training simulations, parts of parameter space that the data prefer, i.e. at the peak of the posterior distribution. We don't waste adding lots of training simulations away in the tails of the distribution. So we find the maximum of the acquisition, we add a training point to that position, we retrain the emulator, we get more accurate determination of the objective function, and this propagates to more accurate determination of the likelihood and the posterior distribution. And we can then iterate that process, adding more simulations until we have converged estimation of the posterior with respect to the emulator model. So we tested that on mock Lyman alpha forest data for a cosmological model. So what you're seeing here is a set of marginalized 1D and 2D posterior distributions for mock data. The true parameter values are given by the gray dashed lines. And then there's two sets of contours. The red contours is not using active learning. So building an emulator, but just agnostically sampling the full parameter space using a sampling scheme called a Latin hypercube. And then the blue contours are using this active learning or Bayesian emulator optimization. And the key point here is that the blue contours are tighter than the red contours. And so we get more, what's happening is that we're getting more accurate determination of the posterior distribution at the peak. And in fact, we do that by using fewer training simulations, but concentrating them at the peak of the posterior. So the crosses are the projected positions of the training simulations, color-coded by the version of the emulator to which they contribute. And the blue crosses are all concentrated at the peak. And so we reduce the emulator error locally where it matters, and we get tighter constraints on the posterior. So we constructed this emulator to emulate how the power spectrum responds to the effect of different dark matter models. And we in particular did this not for any specific dark matter model, but so that we could use it to put constraints on different dark matter models. So we do that by using a parametric model introduced in this paper by Merger, where we have parameterized the ratio of the linear matter power spectrum to cold dark matter using three free parameters, alpha, beta, and gamma. And this plot on the right is then showing how you can fit these different parameters, alpha, beta, gamma, to fit the cutoffs from different dark matter models. So for example, the transfer functions for warm dark matter or ultralight axions. I just would like to say that although we're developing this with a specific case of testing dark matter using Lyman alpha forest data, this methodology is entirely general and is applicable to other emulators of the cosmic large-scale structure. So this is an incomplete list of the many different emulators that are being constructed to analyze different summary statistics of the large-scale structure, like dark matter and halo statistics, galaxy clustering, weak cleansing, also 21 centimeter data. Okay, so let's return to the search for dark matter. And let's start looking for suppression arising from ultralight axion dark matter. So this is a set of marginalized posterior distributions using real data on our nuisance cosmological and IgM model, and then also looking for a bound on the axion mass, MA, which is the parameter on the far right. And we have different contours here, and this time they're color-coded by the iteration in the construction of the emulator. And the key point here is that as I add more and more training simulations, as I go from the blue to the green contours, by the end of that process, there's no statistically significant shift in the posteriors with respect to each other. And that indicates that we have converged estimation of the axion model posterior with respect to the emulator training set. And again, the crosses are the projected positions of the training simulations color-coded by the iteration in which they're added to the training set. The posterior means at the top and the 1 sigma and 2 sigma constraints. And we also have a convergence test, which is independent of the posterior itself, uses what's called the exploration term in the acquisition function. So this acquisition function that decides where we should add training simulations has a term called the exploration term. And the fact that this is tending towards 0 as we add more simulations tells us that we have fully explored the parameter space and found the true peak of the posterior distribution. So this is an important test of convergence in the construction of the emulator. So these are summary results. We have the final results, the final version of the emulator. We have the marginalized posteriors, axion mass on the x-axis, IGM parameters on the y-axis. These are 95% credible intervals. We do not find suppression arising from axions, so we set a lower limit of the allowed range of axion masses. And our dark matter bound, because we've constructed this new emulator, we're able to access a new measurement of the Lyman alpha forest flux power spectrum, which is accessing smaller scales than previously measured, than was used to set dark matter bounds. So these are our data. This is the flux power spectrum as a function of wave number k in the free redshift bins from 4.2 to 5, and the black line indicates the smallest scale that was previously used. And by accessing smaller scales, we can look for the suppression from heavier axions, and so we anticipate improved bounds as a consequence. And that's indeed what we found. So this is the exclusion plot. Each one of these lines is the exclusion on the axion dark matter mass for different experiments. Our exclusion is in green. It's a 95% lower limit, 2 times 10 to the minus 20 electron volts. And that now very strongly disfavors this canonical range of masses that I motivated earlier at 10 to the minus 22 electron volts. So these are the strongest limits on ultra axion to date. Let me just finish by showing the final analysis to these light dark matter models. This is much newer work, so this paper just went up on the archive on Tuesday. And by the same process, so with the same tests of convergence in the construction of the emulator, we're looking for suppression from dark matter proton collisions on small scales. We do not detect that suppression. And so we set a new upper limit on the allowed range of the cross section between dark matter and protons. And so our exclusion is in green, cross section on the y-axis, dark matter mass on the x-axis. This improves over previous cosmological bands by up to about a factor of 25. That's because we're accessing such smaller scales than was previously used. And in particular, I highlight that we're excluding light dark matter regions to which direct detection is insensitive. Anything less than 1 GeV to 100 anything. We expect many more high resolution spectra, which will improve our measurement of the small scale power spectrum, and then by large spectroscopic quasar surveys like DESI, which will pin down the thermal ionization to a much higher precision, and that will help us in looking for suppression from the dark matter particle. And as for axions, this plot is showing exclusion in mass on the
You're cutting out a little bit there, Keir. You might want to give up on your video.
Y-axis and dark matter up the top. Let's turn my video off. There we go. Hopefully this works.
Much better. Much better.
Great. So this plot was showing you exclusions and projected exclusions on axion mass and axion energy density. And you see the strong exclusions for very light masses from CMB and BOSS on the left. These new exclusions from DES, galaxy weak in turquoise, from Lyman alpha forest in yellow. But I in particular want to point out that there's a lot of parameter space still to explore for these heavier ultralight axions. And in particular, this is theoretically interesting because this part of mass fraction space within the black dashed lines would correspond to axion energy scales at the grand unified scale. And so there's particular motivation to go after these subdominant contributions of axions. In particular, a multi-probe approach is needed to fully span this parameter space, combining CMB, galaxy data, and Lyman alpha forest data. So that's all I wanted to say. I'll leave up my summary conclusions, which is these two new constraints on dark matter models, and the work we've been doing to build an emulator model so that we can robustly marginalize over astrophysical uncertainties. So I've finished there. If there's any more questions, I'm happy to answer them. Thank you all for listening.
Virtual applause for Keir. Thank you very much. So we have time for one or two questions. Let's give everybody a moment. Keir, we'll have to have you over at our Space ML coffees here on the West Coast at some point. It'd be great to hear from you.
That'd be great.
Yeah. Okay. Oh, Julio has a question. And Seb. Julio, I think, beat Seb by just a fraction of a second. Go ahead, Julio.
Oh, thanks, Keir, and thanks, Tyrone, for the talk. And it's wonderful to see all these new developments here. I guess I was wondering, these constraints on the quasi-dark matter from subhalos that you had in your, I think, pre-to-last, that comes just from the density of dark matter inferred from dynamical data for some of the ultra-faint galaxies. Is that where that comes from? Or perhaps you can expand a little bit on that?
Yeah, of course. So those subhalo constraints come from the subhalo mass function as inferred from the Milky Way satellite population. So in particular, combining satellites detected by SDSS and also dark energy survey and pan-stars. They now give the tightest constraints.
So just for number counts and not necessarily the internal dynamics of the subhalos, I mean.
Just for number counts. There's also interesting work using strong gravitational lensing. So looking for substructure in strong gravitational lenses. These are very competitive. And stellar streams. So looking for perturbations. And the idea is that these stellar streams are very thin, dynamically cold structures. So any perturbation would be caused by a dark matter subhalo interacting. And these shouldn't exist given a certain fuzzy dark matter mass, for example. And so in fact, some of these groups have done joint analyses with these probes, strong lensing and subhalo mass function, and they're setting the strongest sort of Milky Way constraints.
Yeah. Okay, great, thanks.
Thanks, Julio. Seb, quick question.
Yeah, thanks for the nice talk. I just have maybe a question on the emulator. Do you have, when you emulate such a complex parameter space like that, do you have some specific requirements on your parameter space, or maybe on the differentiability of your models there? Is it, or maybe is it able also to slightly extrapolate outside your parameter space, maybe? Yeah.
Yes, so the Gaussian process is only really good for smooth differentiable functions. So that is the prior that we put on the flux power spectrum is that it's smoothly varying and differentiable. But rather than specifying a particular parametric model, the Gaussian process is essentially a prior over the smooth function space. As for extrapolation, the Gaussian process is not very good at extrapolating. So it becomes important to have a prior on the convex hull of your training simulations. But this also ends up being a physical prior in the IGM, because if you naively set up a kind of cube-like prior on your temperature and pressure, you include unphysical parameter combinations, like very low pressure but very high temperature. But you will not produce that in your simulations, however much you vary the ingredients of your simulation. And so that physically sets a kind of convex hull prior that nicely matches with the properties of the Gaussian process.
Interesting. Thanks.
Awesome. All right. Well, that about brings us to the hour. So let's thank Keir very much again. That was an awesome talk. Virtual applause all around.
Cheers. Thank you.
And
Thanks for the
yeah.